Good morning, everyone. Welcome you to the second day of this winter school of E-PiCo Master.
Morning, Professor.
So during this second day, you will have, as you can see, 4 presentations. 2 in the morning and 2 also in the afternoon. So the first presentation of this morning will be given by Adrien Bourjade.
Good morning, everybody.
The PhD student within the chair between Renault and Centrale Nantes. I am his supervisor. And it will be about PWM control optimization of power converters with applications to EVs and HEVs. You had some lectures, some lessons with him, so you know him very well, I think. Okay, I think Adrien is connected.
Yes,
Adrien, do you hear me?
Yes, I'm here.
Okay. So I think you can start if you are ready.
Yes, I am ready. I will share my screen.
Okay, I stop sharing my screen. Yeah, it's okay. It's for you now, yeah.
Yeah. Okay. So, today a presentation about the PWM control optimization of power converters, and more specifically an application to electric and hybrid vehicles. And to present a little bit myself, I am Bourjade Adrien. I am actually in third year PhD, and I am supervised by Malek Ganes, Maurice Fadel, Jean-Pierre Barbeau, and an industrial partner, Abdelkader Bouarfa, foundation about the PWM control optimization of power converters. And sorry, I have a feedback of my voice.
It's okay, I just fixed it, sorry.
Okay.
Yeah, okay.
Sorry. As I said, Abdelkader Bouarfa worked for Renault, and so this PhD thesis is in collaboration between Centrale Nantes and Renault. So a little bit before starting, just a presentation of what we'll talk about today. So first, an introduction to make a context. So first, an ecological and a social context, followed by an industrial context, and what's the inverter, what is the place of the inverter inside this context. Then a presentation of this inverter, so it will be a recall because everybody here knows what is an inverter. And then we will talk about the literature and about my work, and we will start to do this with the optimal pulse pattern PWM. I will present what it is, and then a more classical one, the Carrierbased PWM, with also work what we did with Renault at Centrale Nantes. And then we will conclude this presentation. So first, the ecological and social context. In 2020, the electrical vehicles represent 10% of the market. So, and this part of the market will be growth in the next years because of 2 main constraints: ecological and social. The first one, the ecological one, because the IPCC, GIEC in French, for French listeners who are here, said that there is an emergency to reduce the global warming process. And the electrical vehicles are in the center of the strategy, especially in France, as the E40 report said. Indeed, in this report, it is written that the vehicles, the electrical vehicles, are ecological as the French production, electricity production, is decarbonized. Furthermore, about the social context, in 2030, thermic vehicle will be banned inside some cities in Europe, especially in London, and maybe in Paris. So about this first context, the electrified vehicles are at the heart of the climate and industrial changes. And so these changes, social and ecological, cannot be done without an industrial constraints and desires will be met. So now just talk about the industrial point of view. And the first one is Renault made electrical and hybrid vehicles. So for now, you learn nothing. And the idea behind my PhD and other PhD doing here at Centrale Nantes, it is to work on optimal software. So here we will not work on the material software because if we can change an optimal software which will have the same impact of than a material change. For example, if we do a material change which costs €1 per vehicle, and if we can do the same thing with the software change, it will save, for example, for €1 change, 3 million euros saved per year, because there is 3 million vehicles produced by Renault per year. Furthermore, increase the efficiency, even a little, is interesting because ecological constraints, the Euro 6D norm, impose that for each excellent gram of CO2 per vehicle per year will cost €95 to the car builder. So it is very interesting to increase the efficiency. Furthermore, for the market, it is very interesting to have a better autonomy because it is the main selling argument for electrical vehicles. Furthermore, better autonomy is ecologically significant because it will reduce significantly the size of the batteries. Me, I'm working on the inverter, but many software are planned to be optimized. And so, because it is integrated into a general way of optimization, even a small improvement inside the inverter is interesting because a lot of other software will be modified. And so if each software increase the efficiency of 1%, 1 little percent, it will have a great impact on the entire vehicle. So as the inverter is the small part of the vehicle, as I said, it is interesting to take a look to what its command will concretely modify in the vehicle parameters. So the inverter can be directly or indirectly have an impact on the efficiency, the weight, the cost, and the temperature. The efficiency and this cost about its structure, because a complex structure, multi-level inverter, for example, will increase the efficiency, but the cost will also increase. The efficiency is directly linked to the temperature because a high temperature, for example, low efficiency will mean a high temperature, and so a high radiator, and so a high weight, and so everything is linked because the more the vehicle will be weighted, and the more the efficiency of the global vehicle will be low, and so the inverter control is not only an impact on itself, but it impacts the whole vehicle and the whole efficiency of the vehicle and on many aspects. So, as I said here, everything is linked. So now we saw the changes on the inverter command can impact the vehicles under many forms: cost, weight, efficiency, and of course, ecologically. We will see now very quickly a reminder of the inverter structure. So here, basically, is a basic inverter with, on the left, the DC source, which composed of a battery and the capacitor. In the middle, the inverter itself, composed of 3 commutation cells, and at the right, a load, a basic load. So here, for example, a synchronous motor. It will be the case for the an electrical vehicle. So about just to recall, an inverter is composed of, this basic inverter is composed of 6 switches. And in practice, we will only do the command on the 3 first switches, the upper ones, because the other switches must be have an opposite way of functioning. So there is, even if there is 3 commutation cells, there is only 3 commands to generate in order to generate the correct voltage, and so the correct current linked to the correct torque or speed at the output of the inverter. In my work, the hypothesis we did are this ones. So 3 commutation cells and 2-level inverter. So a very, very basic inverter. Another constraint for the simulation is a balanced load. So here the load can be not balanced, but here we will do the hypothesis that it's balanced. Another information, it is we will use a stable DC source. So we are not interested here in this work of the variation, the voltage variation of this source. So we will suppose that there is a 4,000 volts in the input, and it will not change. Furthermore, about more technical consideration, no dead time is considered in the simulation, but must be considered inside the concrete application. Okay, so under those hypotheses that I mentioned, we can start with the best PWM strategy, the best one because of its flexibility. We said before that each switch can be commanded by a PWM signal composed of a 0 and 1 signal. And the most flexible PWM is the offline one. And it is why we start with this one, the optimal pulse pattern. So here, the optimal pulse pattern, the objective is to select precisely the times of the switching times. And when we want to select these times, we will consider preferably the angles, and we can convince yourself that an angle is just a time over a period. But even if we can select precisely these angles, they must fit to some constraints because we do not want to do something weird with the electrical motor. So these constraints can be divided in 2 big parts. The first one are the linear ones. The linear ones are very simple. They said that each angle must be succeeded by another one greater and separated of an amount of angle. The 2 other constraints here, UB and LB, means that an angle must be between 0 and 2p because it is a periodic signal, or because our command is a periodic signal. Another constraint, and one of the most important, is the linear and the non-linear constraint. Here we have a modulation index, and we have to fit the voltage reference we desire. Because if we do a PWM control and we do not, and if you have a perfect objective, but we do not have the correct voltage, it is not very interesting. So here we have 2 nonlinear constraints about the Fourier decomposition, and we have to fit the correct voltage, amplitude, and phase. So we will talk of this optimal pulse pattern. We will introduce first 3 main optimal pulse pattern in the literature: the quarter wave symmetry, the half wave symmetry, and next the full wave symmetry. But in order to analyze the performance of these strategies, we need an objective function, and here it is the minimum f of x. It is the objective function. It is what we want to reduce. It is the real impact, the side effect, if we want, of the optimal pulse pattern. And in this specific case, it will be the WTHD, a very classical objective. So here, just a description of this WTHD, the weighted total harmonic distortion. Its purpose is to modelize the effects of an inverter solution on the current behavior. A current behavior, you can be shocked because on this equation here, we do not see any current, but the voltage, the square of the voltage divided by n square is linked with, is proportional to V current, because the impact of an inductive load will be N multiplied by L multiplied by the pulsation omega. This WTHD have advantages because, as I said, it gives an information on current quality. It does not depend on the load and on the inductive load. It is very quick to implement and easy, simple, and easy to read, which is an important criterion. The disadvantage of this WTHD description, if it is poor for a specific application. If you select a precise motor, for example, I don't know, a precise motor, it will be almost sure not the best strategy at the end. But you have the advantage to be general, to be easily applicable, and it have also repercussion on the grid consideration. Another disadvantage is there is no evaluation of the transient period with the WTHD. The weighted total harmonic distortion can be deduced, as we see, and it can be done thanks to the voltage knowledge. So next, we will explicit those equations in order to find to describe this WTHD. And we will start with the three classical OPP, and we will start with the quarter wave symmetry one. So this strategy, this classical OPP, it is the most classical one. It is the first OPP appeared, and the principle is very simple. We will only be interested in the four first switching times, here called alpha 1, alpha 2, alpha 3, and alpha 4. So we only consider switching time between 0 and p divided by 2. And all the other switching times will be deduced from these four first switching angles. Well, by doing so, we have a simplification inside the description of the Fourier decomposition of the command. So here the real part of the Fourier decomposition is equal to 0. The mean value of the command is always equal to 1 divided by 2. And about the complex part of the Fourier decomposition, all the even harmonics are equal to 0. So the harmonics number 2, 4, 6, etc. will be equal to 0 thanks to this characteristic of the quarter wave symmetry. The other advantage of the quarter wave symmetry is there is a few number of decision variables. In this specific case here, we only have 4 switching times called NQP, the number of commutation per quarter period. So here we only have 4 quarter period. Another this command is under also another hypothesis that all the phases are symmetric. So because all the phases are symmetric, the voltage, the third harmonic voltage will be removed. So here we saw computation on a pi divided by 2, but it also exists a computation on a p period. So the equation changes a little bit, and it is what we will see next, but remains similar. So half wave symmetry, here HWS, it is the same principle, but we do not consider only the first quarter period, but we consider 2 quarter period. And so here we have the NQP, 2 number of commutation per quarter period, variable decision. And the main difference here is that we do not remove all the real part of the half waves of the Fourier decomposition, but we keep these properties that to remove the even harmonics. So it is a very interesting property of the quarter wave and half wave symmetry. Some works demonstrated that it is still suboptimal, and we can still improve the WTHD by considering the full wave strategy, the full wave symmetry consideration. Here on the equation, something is very different from the two previous strategies. Here, there is no more removing of the even harmonics. So now the harmonic number 2, 4, 6 or more will not be removed anymore. But because we have a symmetry between these three phases, the harmonics number 3 will be removed. So the harmonic number 3, 6, 9, etc. will still be removed. So past literature shows that full wave symmetry was better than half wave symmetry and quarter wave symmetry. And this was done by always a relaxation of some symmetry constraints. Nevertheless, here it remains a constraint that we mentioned every time previously. This constraint is the symmetry between the three switching phases angle. So a natural idea is to continue this relaxation by considering that the three phases switching angle are different, and this is what we done, and this is what we did, and we call it the Vpsr, the phase symmetry relaxation. To be sure, a good understanding, we do not talk about to relax the constraint on this voltage phase angle, because this one must be respected for the motor, but it is only the three command of the three legs which will be different. So here, as we see, the optimization problem is a little bit more complex, because now we have to consider each phase independently. So here it is an optimization problem for P phases. If we consider three phases, the number of decision variable is very more high than for quarter wave, half wave, or full wave symmetry, because we have this number of variable decision. So it is more than 12 more decision variables than for the quarter wave symmetry. So we have very more decision variables. Furthermore, the Vpsr in the same way than the full wave symmetry, half wave symmetry, or quarter wave symmetry, there is a lot of local minimums inside the solutions. So it is very, very important to have an efficient solver. And we decided here to do a Fmincon based solver. And we have to be efficient because our Fmincon find only a local minimum. So it is very important to have a very good solution starting points in order to find the global minimum, but we can ensure it because Fmincon find only local minimum. So in order to find the better solution we can, we decided to do this strategy. So I will not enter in the complex structure of this algorithm, but just we will understand how it works in the grid lines. First, we will start to have some many random solution x. X is the decision variables. Among these x, we will have a function that will give us the best solution among this big matrix, and then we will store this best random solution inside the list. And for each of the stored solution, we will do the optimization. Furthermore, this list is composed of this random solution, but there is also the full wave symmetry, the quarter wave symmetry, and the half wave symmetry generalized to the Vpsr that are inside this list. And then for each these precise selected solutions for starting points, we will execute the Fmincon resolution that will find the local minimum, and we hope that this local minimum is in reality the global one. So now we have this solver, but it is important to understand that this algorithm is not implemented in real time inside the controller. This algorithm will just afford the best table, a big table with all the switching times and angles. This is the same thing, switching angles and switching time, it is the same. We will store this switching angles inside big tables, and the command, the global control loop of the motor will read these tables and will implement it, and will send it to the switches in order to perform the commutation, the switching. So now the solution we computed previously, we implemented in a real platform, and this platform is represented as we see it here. So classically, there is three main devices inside this experimental platform. Here is the command. We have the real system we comment, and the sensor. We did the computation, the read of the table finally, thanks to a DSpace RTE 1103, and clocked at 30 microseconds, which is a very huge number. And this very huge number forced us to work with very low frequency, with a very high inductive part. And so this command will send it to the inverter disponible at our laboratory, and we work with reduced voltage because, as you know, the inverter can be very dangerous if, especially if we do a short circuit or something like that. And because here we are very all the security are removed, we decided to work to a lower voltage. For this first experiment, we don't want, for the same reason than the voltage, to destroy a motor. So we decided in the first approximation to work with an inductive load and an inductive load connected to a voltage probe, which will be extracted the WTHD information thanks to Fourier decomposition, fast Fourier transform decomposition. Now we saw the Vpsr experimentation. We will see what kind of results this configuration provides. So here we have a WTHD representation of the PSR strategy. So with phase symmetry relaxation, the strategy we found in our laboratory, and the full wave symmetry, the literature-based optimal pulse pattern for the WTHD. Here we see that we recall the what is the modulation index, and the modulation index here is just the percentage of use of at the output of the DC source. So here this modulation index is represented on the x-axis, and the percentage of WTHD is represented on the y-axis. What we see with these results that it is that even if Vpsr is not the best strategy for all the modulation exists, for all the modulation index, it is at least good, at least as it does not decrease the quality of the full wave symmetry. It is what we see here, and does not decrease the quality for a lot of modulation indexes. But, and here it is the most interesting part of our strategy, it is that increase the WTHD results for a modulation index greater than 0.5 when the number of commutation per quarter period is equal to 2. But this result is not found only for the number of commutation equal to number of commutation per quarter period equal to 2, but this observation can be done for many other cases as NQP, the number of commutation per quarter period equal to 3, 4, 5 or greater. But we must be sure that we cannot increase an infinity of a number of commutation per quarter period, because if, for example, when the number of quarter period is equal to 10, the impact of our strategy is negligible because the voltage harmonics are high enough to be directly divided by the n factor of the WTHD equation. So here, a representation of the same graph as previously, but for a number of commutation per quarter period equal to 5. Previously, it was for 2 commutation per quarter period. And here, the improvement zone is different, a little bit different than for a commutation equal for a number commutation equal to 2. It is interesting to see the difference, the more quantifying difference of this WTHD improvement. So we decided to do the mean of the WTHD, so mean value on the whole operating points, and that we see that the difference between the Fourier symmetry and the Vpsr on the whole period is there is an improvement, but we agree together that this improvement is quite small. But it is the effect of a mean value. If we look more precisely to the relative improvement on the specific improvement zone, we see that we can reach, for example, for when we consider 2 commutation per quarter period, we can reach 16% of improvements between the Fourier symmetry and the Vpsr, and 16%. If we remind my introduction, it is very important because we said previously that even 1% was interesting because our software is just is concerned about just a tiny piece of the entire global powertrain of the vehicle. So even 1% is interesting. So another remark here is for NQP equal to the increased percentage is higher than for the when NQP equal 5. It is understandable because when we have higher switching frequency, the harmonics will be higher, and so the WTHD will be naturally decreased. So these results are based on an algorithm presented before, itself based on F-min-con, and this algorithm find only minimum local minimums. So how to be sure that the PSR curve showed here is really based on an asymmetry of the angle and not a best full wave symmetry local minima? Because here, for example, perhaps the full wave symmetry I present is just a full wave symmetry, and the PSR is another local minimum. And we have the proof here. The proof is represented on this second graph here. We see that the harmonics number 3 and 6 are not removed. And we see in the previous equation that if we consider symmetry between phases, the 3, 6, 9, etc. harmonics are systematically removed inside the Fourier spectre. And so you see that there is the harmonics number 3 for Vpsr is not equal to 0. So the algorithm we presented before rarely converge to a PSR, so asymmetry between phases, and not only to a full asymmetry, but with a better local minimum. The other graph I said is here to in a pedagogic way, because it is very difficult to see what will be in the impact of the PSR against the full wave symmetry just regarding the voltage. So it is very important to see the Fourier decomposition to be sure that the impact of our strategy is better. Okay, so now we see the OPP and the optimal plus pattern have the disadvantage to be hard to implement inside a car and necessitates to recycle the entire board computer to introduce an FPGA, for example, because why an FPGA? Because it have a very high speed way of functionment. And this FPGA introduction enter in contradiction with one of the objectives presented in the introduction. Yes, in the introduction, we said that we want to limit the number of additional material inside the car. And it is why we decided to also study some synchronous carrier-based PWM. So what is a carrier-based PWM? So I will do a quick recall about this kind of PWM. And so here on the left, you see three types of signal. You recognize in orange the PWM, and the PWM is deduced thanks to the comparison between the carrier in green and the modulation signal in blue. The modulation signal is composed of the reference of the signal, VRF here, plus a zero sequence component, which can be different. It can be equal to 0, it can be equal to many other possibilities. And some of these strategies of these zero sequence component possibilities are represented here. This carrier-based PWM list is not exhaustive at all, and there is a lot of strategies developed inside the in the literature. I just want to say that this carrier-based PWM is just a little bit special in my case because it is a synchronous PWM. What is a synchronous PWM? That means that the switching frequency is directly linked to the fundamental electrical frequency. So here the switching frequency is equal to 2 multiplied by the NQP, the number of commutation per period, multiplied by the electrical frequency. Indeed, historically, in the past, the PWM, the carrier-based PWM was analogical, and the switching frequency is set to a very high number, and then it is fixed. Here, in this work, it is not the case. The switching frequency is not fixed and will vary thanks to the electrical frequency, and the electrical frequency is directly linked with the speed of the motor, and so the switching frequency is driven by the speed of the motor. So among all these PWM strategies that I mentioned, some of them are more used than the others, and it's the case of the SVM and of the third harmonic injection PWM 1 divided by 6, the THI PWM 1.6. So here are those two strategies. The SVM is the most used in the literature and by extension in the industry because it has the great advantage to be vector-based. And this vector-based property is very interesting when we are driving, for example, a motor. So this SVM control can be transformed into a carrier-based PWM by an injection of a zero sequence component. In the same way, this third harmonic injection PWM 1.6 is the injection of the harmonic number 3 by with an amplitude of the desired reference divided by 6. But there is something important that I do not mention is why do we do that? Why do we don't just do the injection of the reference signal inside the modulation, and we just do that and we see what happened. In fact, the literature knows from the beginning of the 20th century that it is suboptimal, and doing so with the SVM or the third harmonic injection PWM 1.6 increase the maximum voltage possible inside the load. By doing so, it's mathematically increase the harmonic quality, and this harmonic quality, we saw it, is highly linked with the current quality and then the efficiency, the WTHD, and furthermore, the losses. So about the third harmonic injection PWM 1.6, we wondered why we limited ourselves to only one single injection in the zero sequence component. Because here we inject the third harmonic injection. Why? Because as we saw previously, the third harmonic have no influence on the output of the load. So we decided, in my PhD, we wondered why only one third harmonic was considered, and we decided to inject theoretically an infinity of third harmonic injection PWM, and it is what we call the zero sequence component modulation. So as I said previously, the idea is to do the same than a third harmonic injection PWM, but with more harmonics. So we do not only consider now three harmonics, the third harmonic, but the harmonic number 3, 6, 9, etc., etc. Now we have the idea under this zero sequence component, but in practice, how we will implement this strategy inside an optimization problem. We will do that thanks to a Fourier decomposition. This Fourier decomposition, here we will compute the amplitude of each harmonic of the zero sequence component. And thanks to this knowledge on the harmonics, we will deduce in time the waveform of the zero sequence component. So thanks to the Fourier decomposition, here we have the third harmonic, the 6-1, 9-1, the 12-1. We will, thanks to this equation, so the zero sequence component is equal to the mean value of our strategy plus the Fourier description of a signal. Then, thanks on this zero sequence component thanks to this zero sequence component reconstructed, we can compute, thanks to the same principle than a classical carrier-based PWM, the switching angles. So now we have reconstructed the zero sequence component in time. We can add it to the reference signal here, and we will have the corresponding modulating signal. Here, for the example, this modulating signal is really near the zero sequence, the SVM equivalent, in order to be more clear. Then, thanks to this representation, we will compare it to a synchronous carrier signal, and this synchronous carrier signal will give us the switching times of our inverter. And so, doing so, you can convince yourself that this is exactly the same thing than an extended third harmonic injection PWM. So, as for the Vpsr, we saw previously, an optimization problem is needed, and luckily for us, this optimization problem is really near Vpsr1. So this optimization problem is represented here. So as previously, as for Vpsr, we want to minimize an objective function. So for example, the WTHD or the losses, and we want to meet the desired voltage, because if we do not meet the desired voltage, our strategy is null. It corresponds to nothing and can be implemented inside a motor, and so it is very dangerous to implement a strategy that do not fit these constraints. So the optimization formulation, as you see it, is very near Vpsr1. And so thanks to the previous algorithm we saw previously, we will be able to compute the solution. And we did some lot of experimentations. So about the WTHD, we do experimentation about the losses, etc. And at the moment, we discovered something very interesting and something very curious inside the waveform found. These waveforms. So here are the waveforms found for some RL load, but more specifically the losses. So here, when we consider only the switching losses and when we consider the total losses, and perhaps there is something that shock you too. It is this specific waveform. We have here some discontinuities. We have a Gibbs effect which appears, but it looks like, it really looks like if we have a sawtooth PWM appearing in our strategy. And we have this intuition, and we confirm this intuition by doing an optimization problem. So we add sawtooth description, we add the zero sequence component description, component modulation description, and we try to match together. And we discovered that the sawtooth PWM is just the natural, if we try to converge the zero sequence component with an infinity of harmonics, the zero sequence component we found will converge to a zero sequence component for some specific operating points. And so by doing the zero sequence component modulation, we found a new kind of strategy, a new kind of classical strategy, if I can call it this way. It is the zero sequence, the sawtooth PWM. And so we will, and so let's talk a little bit about this sawtooth PWM. This sawtooth PWM is very easy to implement because it only depends on two parameters. So a very easily way to find a solution. So we have the minimum of the sawtooth, the maximum of the sawtooth, and because we must have a third harmonic property. We know when the discontinuities are, and so it is a very easy way to implement. So we did the optimization. We decided to test the strategy with WTHD and velocities, and so I represented here the way we compute velocities. So they are composed of the switching losses of the strategy, the conduction losses. So the switching, it is when we stop to compute, when we change off from 0 to 1 or 1 to 0, and the conduction losses are due to the conduction losses when the switching is high. And so thanks to this description of the losses and the WTHD, we decided to implement it inside our platform, the platform described for Vpsr, and we obtain this kind of results. These kind of results are very interesting because we see that the zero sequence component modulation and the sawtooth are better than the two previous solutions, so the SVPWM, the SVM, but the SVM on the carrier-based SVM, and on the third harmonic injection PWM 1.6. And both of the sawtooth PWM and of the zero sequence component modulation are better than the classical strategies. But because there is a negative impact, there is a negative point of this strategy on WTHD, it is that works only when the number of commutation per quarter period equal to 3. When the number of commutation per quarter period is equal to 4, 5, more or 2, there is no positive impact of sawtooth on this on WTHD. The zero sequence component modulation succeed to improve a little bit the WTHD for other operating points than NQP equal 3, but we decided to do not show them here. So as I said, we also did losses modelization, and this losses modelization was tested only in simulation because for now we are not setting in order to compute precisely the losses. And so we saw that the sawtooth, as we mentioned previously, the sawtooth will improve to a very high percentage the classical third harmonic injection, because here this increase in percent is the increase of our strategy against the third harmonic injection PWM. So the zero sequence component modulation is better than the third harmonic injection PWM, and the sawtooth is also better than the third harmonic injection PWM because the percentage increase is greater than 0. Furthermore, we remarked that inside the zero sequence component modulation, the sawtooth the mean value of the sawtooth is almost never equal to 0. And what does that mean? That means that it behaves a little bit as a discontinuous PWM. So to conclude this part, this losses strategy give us a good presumption for the sawtooth PWM, sorry, but it must be tested in practice. So now a more global conclusion. So as we saw in the introduction, the software improvement is very important. It will be for Renault, but also for the ecological. So our strategies looks to the future. And it is you can convince yourself that any changes is meaningful, as I said previously. In my PhD, we found for now three different strategies: 2 carrier-based PWM and 1 offline PWM. And what is very interesting, it means that the most simple inverter, the 3 phases 2-level inverter, which is very well known in the literature, does not give us all its secrets. There is still secrets on the inverter that must be discovered on this very simple device. And so I will finish this conclusion by saying that even this simple device, this simple inverter composed of 3 phases and 2-level can be really improved by in future works by carrier optimization, by example, or we will prove that our sawtooth PWM is very efficient in order to feed the motor, PWM motor angle observation, or I don't know. It will be the role of researchers to find this new strategy, but the field is really open and have a very and is really meaningful for our future. Thanks for your listening.
Okay, thank you, Adria, for this clear presentation. Yeah, now we have time for a couple of questions. So if you have any questions, you can ask them to Adrien. Yeah.
Hello. I just want to ask that for the load, you used inductances as a load, but how different could be the results if we use a real motor? Or what can expect if the results are very different?
In fact, the advantage of this kind of strategy that I presented is this thing. This thing here, you have the optimal description. You have this algorithm, this objective function, this description, and basically, the only thing that will change if you want to consider a motor is this part. You define precisely the objective function, and if you define it, you can define it as whatever you want. And by defining this as a real motor, you can, if you compute with thanks to your modelization, a very efficient DQ, for example, model, it will have only an impact on the objective function. So what I described here is very you can recycle it for every application. So if you want to minimize the losses, if you want to minimize the noise, if you want to minimize the harshness, you want to minimize, I don't know, you just have to change this minimum function, this objective function, and you will be able to solve it. Us, because of our experimental restriction and because of the safety of the experimentation, we decided to limit for now, we decided to limit to WTHD for this specific PSR test. But very next, we will hire an internship student in order to do this on a real motor, and so he will have to he or she will have to implement it on a real motor, and so considering this DQ or motor modelization, and then modify this objective function. Do I answer to your question?
Yes, thank you very much.
You're welcome.
Yeah, yeah. I can see a question on the chat, Adrien, for you from Atarva. The question is about F-Mincon. If you can explain the optimization function F-Mincon that you have used.
F-Mincon function is a little bit a black box, in fact, because it is a toolbox provided by MATLAB, and so F-Mincon is just a very good constraint local minimum finder. And in practice, I do not enter inside the really how it works, but it finds a local minimum and the correct one, and I set up the parameter to SQP parameter. So I don't remember what does SQP mean, but I can find it if you want. But right now I don't remember how works precisely F-Mincon.
Okay. Okay, we have still a few minutes for questions.
Mm-hmm.
If you have further questions.
Hi, Adrian. Hi, everyone. Good morning.
Good morning.
I would like to ask about something that wasn't clear for me related to the PSR and the FWS. When you mentioned about the harmonics, which one should contain, because I saw that the FWS doesn't contain all the harmonics and the PSR contains, and I didn't understand if they should or should not contain the harmonics, and what are the implications of it?
It is not a case of containing or not containing the harmonics, because in fact this harmonic is just depend on here the alpha G, and the alpha G are the switching angles. Okay, so here when you consider no symmetry on a phase, okay, this function you see here will be described by this Fourier description. Okay, and so the PSR1 will have the same description, okay, but on these three different phases, and the three different phases will have different alpha G, and this property will have a negative impact on the third harmonic, and it will not be removed anymore. Okay.
Okay.
So I am not sure I am clear, because it is a very mathematical understanding, but you want to keep in mind that the classical strategy, it is true for the quarter wave, half wave, and full wave symmetry. Each command of each leg is the same, really is the same, but dephased. Okay, so you just add on this switching times, you just dephase it from of 2p divided by 3, and so you will and so it will be your command for the two other legs. But for the PSR, it is not true, and because of it, the third harmonic in the voltage will not be removed.
Okay. No, it's just I think it's another graphic in the presentation where you have like the comparison of the between the two methods. I don't know if it's further or back, where you can see like the voltage graphs, and also this one, exactly this one. Yeah, because before it says that the FWS no harmonic is removed, right? And here I can see that there's Yeah, there's like the 2, the 3rd, and there is the 2 and the 4th harmonic, right?
What I said previously, it is in the full wave symmetry. It is an abusive language to say V2 and V3 are no harmonics are removed. In fact, when I say that the no harmonic are removed, this is in comparison to the quarter wave and the half wave symmetry. The quarter wave and the half wave symmetry impose that the 2 and the harmonics multiple of 2 and multiples of 3 are removed. So for a quarter wave symmetry, for example, the harmonic number 2 will be equal to 0. The harmonic number 3 will be equal to 0. 4 also. 5 not, 6 yes, etc. So all the harmonics multiple of 2 or 3 are removed for a quarter wave and half wave symmetry.
Oh, okay.
And for the full wave symmetry, the harmonic number 2 are not removed, but the harmonic of the multiple of 3 are removed because of the symmetry.
Okay, okay.
And when we do the PSR, the harmonic there is no systematic removing of harmonics. So for in this specific case here, the PSR strategy decided to set an harmonic number 3 not equal to 0, which is the case for the full wave symmetry. And for the full wave symmetry, it is necessarily equal to 0 because of this angle symmetry.
Okay. Okay. Thank you very much.
You're welcome.
Okay, we have time because to ask further questions, because the next presentation will be at 10:30. So you can ask more questions.
Is there no question? We can drink a coffee.
Yeah, but we cannot do it remotely.
Yes.
Okay, where is Hassan? Abid? I don't see him.
Yeah, he is connected.
He's connected? Hassan, you work about optimization methods.
Yes, sir.
Yeah, you can ask a question about it for Adrian.
Yes, I can see Mr. Adrian have used this F-mincon function, which is a MATLAB nonlinear constraint solver. So I also have experience to work on these functions. But Mr. Adrian, I have a suggestions, not suggestions, actually, I want to give you an information that if you are working on Python, in Python, you can also have these optimizations functions solver. I think mainly this is a Rosenberg function. The options to use the Python-based function is more convenient than the MATLAB function. So you have it's a customized function in Python. So if you have a chance to try this one, I think it will be a good experience for you.
Okay, thank you. I will consider it, but there is just the main constraint why I use MATLAB. It is because of the experimental platform. As I said, the RD space works with the MATLAB Simulink, and so it was more convenient because of the interface to work with the MATLAB Simulink. And so you are perhaps right. Perhaps I lost a lot of time by doing this algorithm because F-mincon find only poor local, no, not poor, but only find the local minimum. Yes, perhaps Python will be better. And for sure, I will consider your advice because I remember at the beginning of my PhD, I was searching for F-mincon global optimization, but it is in the global optimization toolbox. But it was expensive, and so we decided to do it manually if you want.
So basically, you just use the MATLAB commands, MATLAB libraries for optimization techniques, and the function was not being modified in your cases. Is it right?
FMINCON, no modification. So we just FMINCON is rarely used as a black box.
Okay. So, sorry, you already have mentioned this in your presentation that you used it as a black box. Okay. Thank you, Andrew.
You're welcome. You're welcome.
Okay, and another questions? Okay, maybe Adrien, you can say some words about the implementation of your method on real setup.
Okay.
With a real power of like EV car or HEV car.
Yes, actually, we are talking about just an information about next work. We are in direct link with the Renault Research and Development Department on electrical vehicle and control. And they will provide us, they already provide us an electrical motor with an inverter, and they will provide us a FPGA platform with the DSpace, and this DSpace plus the FPGA platform will be implemented inside in order to drive the EV HEV motor. But as I said, I am third year PhD, so I will not have the full time to consecrate to this problematic. So with Malek and my other supervisors, we decided to hire an intern in students to do an internship inside this problem. So he or she will have to develop VHDL software in order to control the inverter. This VHDL is required because, as I said, here we work with very low frequencies, and everybody here understands that it is not acceptable to work at so much lower frequency. So we have to increase the speed of our device, and it is why we considered FPGA. And Renault was agree with this requirement, and it is why they will provide us soon, I think in some weeks, before the end of the month, normally, the platform.
Very good. Okay, if you have another questions. So this part will be helpful for you when you will move to another partners for the second semester of the master. You will have lessons about power electronics and all these issues, elements presented by Adrien will be helpful for you. Okay, yeah, I think there is a question on the chat. Okay, let me see this. From Atarva again. Okay. While performing the Vpsr experiment, you told that you used inductors rather than motor. Could you explain what would have happened if motor is used a bit?
I think I already answered to this question. No.
You answered to this question. Okay.
Yeah, because it is the same question. Then I think this person asked this question loudly. Am I right, Attar?
No, it's not someone that's connected on the Zoom meeting. He is on the YouTube platform.
Ah, okay.
Yeah.
So I can explain again if it wants. So as I said, we consider here an inductive load because of safety problems. Indeed, we work with an inverter. If we do nothing, if we do something very bad with our inverter, it can destroy the load. So in the first approximation, we decided to do this with a very low voltage and with the very and with the load which is not a motor. But as I said, if you want to, when we will have the platform of Renault, we will work with the real motor. So it's just a question of time. It's just a pre-process of here we consider an inductive load just as previous result. I don't know how to say primary results. But soon a motor will be considered. It's just
but I think behind this question, Adrien, there is also the fact that if the load is not inductive, for example, you can have a capacitive load, not for example a motor. Your method still work. So this is the main important issue that you can precise.
Yes, yes, you are right. Indeed, in the optimization here, nothing change if we consider a capacitive load fed by an inductive source. It is exactly the same problem. So we decided to present this phase symmetry relaxation problem as a very generic one. So here it is why we wrote f of x, so a very generous general function, and which can be tuned by the reader. And here the Fourier description constraints will be the same almost the same for a capacitive load fed by an inductive source. So yes, there is no difference between my inductive load strategy and the capacitive load. But why do I presented only the inductive load? Because we are in the case of an electrical vehicle, and so it is a motor is very inductive.
Yes. Good, very good. Okay, another questions?
Okay.
Yeah. Also, there is an issue, Adrien, by working at low frequency switching.
Oui, yes.
What is the benefit for EV, HEV applications? cars.
Yes, in fact, working with the low switching frequencies, so low NQP, as I said, in practice, when we have a fixed switching frequency with the carrier-based carrier-based PWM, when you are at the high speed of a motor, when F1 is very high, the frequency is very high, the switching frequency, the ratio between the switching frequency and the fundamental frequency will be very tiny. So our strategies, even if for the constraint I mentioned, we work with a very low frequency, the objective at the end is to use this strategy to when the electrical frequency and so the motor speed is very high, and so we are limited with the switching frequency ratio between the switching frequency and the fundamental frequency. And so our strategy will be used, in fact, when if we imagine in the real world, inside the highway, for example. So when we are on the highway, your speed is very quick, very fast, and so the switching frequency the switching frequency ratio will be very low, and so it's here where my strategy have a very good impact, because when the switching frequency is very high in front of the fundamental frequency, to be honest, my strategy are not very good in the fact that the harmonics will be so high they will be completely negligible. So my strategy are only interesting for low switching frequency. And this low switching frequency have another advantage, that they will have the more your switching frequency is low, and the more your switching losses is low. Yeah, and the more your switching losses will be low. And so there is another advantage of this strategy. It is that we work with low switching frequency losses, but of course the conduction losses will increase.
Yeah, behind this issue, Adrien, yeah, you have to take care about the efficiency.
Yeah, of course.
Yeah, this is why it is very important to say. So it's linked to the losses, of course.
Okay, yes, of course.
The efficiency is very important on HEVs cars to be marketed. You have to respect, the efficiency of this
yes.
cars.
Efficiency, in fact, is what interests customers, because higher efficiency will means higher autonomy. So it is the heart of the problem, the current problem of electrical vehicles, to have a small battery with a very good efficiency and so very good autonomy. It is the main problems, I think, of the electrical vehicles.
Yes. Another questions? Yeah, maybe another question, Adrien. Did your method works for multi-level inverters?
If for multi-level inverters, my strategy works for as I said, for every inverter with the P phases. For multi-inverters, it will be more complex, because this problem will be redefined, but it will be redefined with the constraint and about the reference, which will not be exactly the same. So my strategy, yes, it is perhaps a problem of my strategy. It must be redefined if we want to work with the multi-level inverter, because the voltage does not behave the same. There is some little bit problem, but this strategy, as described, worked for any voltage P phases. sorry, inverter P phases.
And yeah, and maybe another question.
Mhm.
If the phases are not balanced, for example, if you have the angle of phase which is different a little bit from 2π/3 for three-phase system, or 2π/p for p-phase systems, what happens in this case?
In this case, if it is not balanced, I think we do not evaluate it. So it is just an understanding with the ends. So if the phases are not balanced, V current will not be correctly described by the WTHD. I think it is something quite clear, and if the phases are not balanced, I think the Vpsr could be very interesting, because we can pilot differently the phases, and it is a very great advantage of this strategy.
Yeah, interesting. Okay, other questions? We have still 10 minutes till the next presentation.
They can go search a coffee, for example.
You want to drink coffee, right?
Yeah, I do not drink my coffee of the morning, so I need one.
Okay, so you can do it.
But I must leave, so if there is any question, I must be here to answer.
Yeah, yeah. Okay. Yes. Can we use these techniques in PMSM?
PMSM?
This is a question from the chat from
Permanent magnet, yes.
Yeah, of course.
Yes, yes, as I said, yes, we can use this strategy on PMSM. As I said, we do not work with the PMSM for the simple reason that working with PWM directly can be dangerous if our strategy, if the computation I did was not correct. If I made a mistake in my simulations, it would be very dangerous for the motor. And so we decided to do not work for a PMSM, but of course, yes, and it is done to work for PMSM. And inside this slide here, the 12.1, if you want to work with the PMSM, your PMSM, I don't know what are its characteristics, you write on MATLAB or Python or whatever you want your objective function. So I don't know, you use the DQ parameters, and you have your parameters LDLQ, and you compute efficiency thanks to your inverter knowledge and your PMSM knowledge. You implement it inside your minimum function here, mean of the objective function, and then your strategy will work very good for your specific strategy. Yes.
Yes, maybe the question behind this. Yeah, the issue behind this question is that to now, if yeah, the phases are synchronized with the position of the motor.
Yes, of course, because the voltage reference will be synchronized. So yes,
will be synchronized. And if you deal with non-synchronized voltages with the position, for example, if you have an induction motor, what happens in this case?
If I have an induction, To be honest, I don't know, but my hypothesis is that it changed almost nothing, because it will be the same problems than for the classical optimal pulse pattern. So I do not know how it will behave in this specific case, but probably the same than the classical OPP.
Yeah. Okay, let me check if there is any more questions.
I would like to ask a question. It's
Yeah.
more generic. My name is Saurabh, and I wanted to ask, what is your, personal experience with doing a PhD? What was your motivation, and what challenges have you faced, and what do you hope for yourself in the future?
Okay, so you want
Very
to
good
know,
question.
you want to know about okay, you want more about me. So me, at the beginning, I would work inside a medical robotic surgery, and I do an internship in this field. And at the end of my internship, I decided to do a PhD to be an expert. And so here you see that it is very, very, very different than surgical robotics. And it is because this subject, I found it was very technical, with three main things, which is control, electrical engineering, and mathematics and applied mathematics. And so I found in this PhD a very interesting opportunity to become an expert, because a PhD student, it is to be an expert. Don't be scared about the words. And so I think I choose this PhD because of this subject, which mix all my my engineer background, my engineer, what I did in my past work. And so what is the most difficult thing inside a PhD? I think it is the autonomy and the and to do things by yourself, and to do not be scared about the time that it will take. Because when you do research, when I start to work on phase symmetry relaxation and on the algorithm that I presented, etc., I was not sure at all that it would work. Perhaps full wave symmetry was already the best strategy, and it was very scared. And sometimes I was wondering if I was not losing time, because I was no certitude it will work. The same thing for the zero sequence component modulation. I have no idea that I will lead to sawtooth PWM or something like that. So yes, the most scaring thing is the autonomy and the because you are inside terra incognita, and so it is it's a little bit frightening.
Okay.
Do we answer to your question?
Yes. Thank you very much.
Okay. Thank you for all this discussion. Interesting topic. Thank you again, Adrien, for giving us this talk about your PhD thesis work. And now I think the next speaker is connected, so we can move to the next presentation from Renault. Okay, will be given by Ludovic Merlin.
Hello.
Hello. Good morning, Ludovic.
Hello. Good morning.
So I think you have the right to share your screen, and thank you again for coming to give us a talk today.
Okay, it's my pleasure. Oh, yeah. Okay. Do you see my screen?
Yes.
Talks. Okay. I'm Ludovic Merienne. I work in Renault, and I'm an expert in system control and control design. Now I work for Renault. It's been for almost 12 years. So it's a bit long. And mainly I work on the project E-PiCo, which was finished almost 2 years ago. And it's a project regarding hybrid technology. It's the first hybrid vehicle we start to sell for Renault. So hybrid is now mandatory for CO2 emission. You see what we project in the next years coming. It was really a few EV vehicle and mainly HEV, but we expect that you may know that in 2030, thermal engine might be forbidden. So in 8 years, we expect that all this vehicle will be only EV, and hybrid will maybe use hybrid with hydrogen. And we are talking to keep hybrid with thermal engine, but only if the emission is really low. So it will be difficult, but we are working to adapt to this new world without thermal engine. Here, this repartition was 2 years ago. So EV are increasing really fastly. Hybrid also, but we fear that hybrid will reach a maximum in a few years coming, and then will decrease because of this 2030 law we expect to appear. So maybe in the next 10 years, EV could represent 100% of a vehicle we will sell, if we consider that hydrogen vehicle is EV also. But with hydrogen, we need also to have a battery. So in my point of view, hydrogen can be seen as a hybrid vehicle, but which don't emit CO2, but which create only water, H2O. Okay. Just to see. Okay. I don't know if you have any question or remark. Feel free to ask during my presentation. I think it's better to have an exchange. So
yes,
don't hesitate. Okay.
Yeah. For the student, feel free to ask questions if you have any question. Don't hesitate to ask them to Ludovic.
So I will start to present E-PiCo technology, and then we'll go deeper to topic such as gearbox control and adaptive E-PiCo and dog clutch management, as you will see. So 2 years ago, we start to sell those 3 vehicles using our new technology E-PiCo. Some are only HEV, hybrid vehicle, and some are plug-in hybrid vehicle. And so regarding E-PiCo, you can see here that we have a thermal engine and the gearbox, an electrified gearbox with 2 e-motors. as you can see here. The main one. So here I will start by the new gearbox, which use dog clutch. It means that there isn't any normal clutch and there isn't any speed synchronizer. Dog clutch technology is the Formula One technology, as it has the best efficiency, but it was well known to be not so comfortable. But that was a big part of my work to control this gearbox and to make it feel as comfortable as now a dual clutch gearbox. And I can say that we have reached this objective. So,
sir, this is MD Abidason. I have a question.
Yes.
As you said, this type of gearbox has the maximum efficiency in terms of what? And what is your measurement? Why are you saying this?
Oh, it means that the loss of the gearbox are really low in a manual gearbox. When the motor are creating maybe 20 kilowatts, the efficiency is almost 95%. Means that we lose 5% of the power at the output of the gearbox, mainly because of the speed synchronizer. Here in this gearbox, we reach an efficiency of 98%.
So, sir, as you maybe you're saying that the input and output relationship of the gearbox is almost linear because
yes,
the loss. Okay.
Because the loss are really low, and
and you're not using any oil inside the box.
There is a little bit of oil. Yes, that's why we have 2% loss. But the loss are divided by 2 or even more comparing to other type of gearbox.
Okay, sir. Thank you.
And as there isn't any clutch, also a clutch also has an efficiency. And here, as there isn't any, we can consider that we replace the efficiency of a clutch, which is mainly around 96%. Here, as we don't have any, it is 100% efficiency.
So, sir, this is the point that I have doubt that is there any machines or any system that can give you the efficiency of 100%?
No, it's figurative. It's figurative here because it means here the gearbox doesn't have 100% efficiency. As I said, it is 98%. But when we see what could I say? A typical gearbox, it means that we have the gearbox and the clutch which is linked. The gearbox has an efficiency of 96%, and the clutch has also its efficiency, which means that we have to multiply those efficiency, and we add the loss of each part. As here we don't have any clutch, it means if we want to compare with a normal gearbox which has, it means that here the gearbox part have a lower loss, and the clutch part, as there isn't any, we can simulate it or represent it as a fictive clutch, which has an efficiency of 100%. But this is only because we don't have any clutch.
Okay.
This is not real. It's just to compare with
conventional
older technology.
Yes, conventional gearbox. Okay.
Conventional gearbox, yes.
Yeah. Makes sense. Okay, sir. Thank you.
Okay. So connected to the gearbox, we have a traction electrical motor, which can be used to go even to 130 kilometers per hour. Here, what we sell, this electrical motor has a maximum power of 52 kilowatt. So it's not so big, but enough to reach the maximum speed allowed in France. And we have a second electrical motor, smaller, which is connected through the gear, but directly connected to the thermal engine. Its maximum power is 27 kilowatt, but in very few cases, the nominal power is only 20 kilowatt. But this motor can also be used to drive the vehicle, as it is connected to the thermal engine, and the thermal engine can be connected to the wheel through the gear. So our thermal engine is a straightforward atmospheric. So
excuse me,
yes?
I have a question in your last slide.
Yes.
So are you like, is it possible to use the main motor for in as a generator as well while you are using the thermal engine instead of the smaller motor?
Yes, I will show it. We can do almost everything with this gearbox, but I will show all the possibilities.
Okay.
I have a slide later.
Okay.
I will show. So thermal engine, nothing new. In fact, we use a motor which was designed several years ago from Nissan for Nissan's first hybrid. So it is an engine with efficiency was optimized, but not so much. Now we are working on a new thermal engine with better efficiency, especially in hybrid use. And what is interesting with this gearbox is that it can be used as a simple hybrid vehicle. It means we use it with a small battery, but it's the same thermal engine, the same e-motor, and the same gearbox. If the battery is small, I would say capacity of 400 watt hour, it is a hybrid. And if we put a bigger battery, our plug-in hybrid battery is almost 9 kilowatt hour. And that's why our technology is simple to adapt as hybrid or plug-in hybrid. So even if it is the same e-motor, depending on the battery we put, we cannot use it with the same level of power, because with a smaller battery comes a smaller voltage. Our big battery has a nominal voltage of 360 volt, whereas the hybrid battery has a nominal voltage of 240 volt. So even if it is the same e-motor, because of the lower voltage, we are more limited with the power. So with a hybrid battery, the e-motor is limited to 30 kilowatt. And with a bigger battery, we can use it with 52 kilowatt. That's why, even if it is the same gearbox, same motor, when we sell it as a simple hybrid, we deliver with all the motor 105 kilowatt maximum power, and for plug-in hybrid we can reach 120 kilowatt. This is only because the e-motor can deliver even more than here the difference is only 15. We could have here put maybe 130 kilowatt, but we choose to limit to 120. Why? Because when we use a plug-in hybrid, if the user charge often its battery, in this case, the voltage remains higher, and we could almost always use the main e-motor with maximum power 52 kilowatts. But if we are facing this issue, a lot of our customers don't charge their battery even with a plug-in hybrid, and by doing so, the gearbox cannot optimize as much as if the battery is fully charged, and we are a bit more limited. So this 120 kilowatt is the power we can for sure deliver even with a low charge of the plug-in hybrid battery. But as I said, if the customer often charges its battery, he will have, in reality, 130 kilowatt of maximum power. But for homologation, we have to homologate with the worst case. So here, the worst case is a customer that never charge, that never plug its battery. It's a bit a shame to not to never charge a plug-in hybrid vehicle, but we cannot force our customer to use it. Okay. So just for your information, our full hybrid model, we sell it on Clio with this performance. Just for information, it is interesting to see that what is the gain with a hybrid gearbox. Here, the emission is 96 grams CO2 per kilometer. To compare, we sell this car with non-hybrid technology, and the emission is about 110 grams CO2 per kilometer. So you can see the difference, and again with the hybrid gearbox. And because of homologation, our objective is to go below 90 grams CO2 per kilometer. That's why we are still working on this gearbox and e-motor and battery and engine and thermal engine to continue to increase the efficiency. And next year we will re-homologate the car, and the emission will be 88 grams of CO2 per kilometer, which leads to a big tax reduction for Renault. That's why we are working, in fact, to avoid tax on this CO2 per kilometer emission. So here you can see how is integrated the motor. So the gearbox, as we gain some place, because there is no clutch, and this and this dog clutch gearbox is really small. Everything takes place in the front of the car as a conventional gear and thermal engine, and just the battery, we put it in the back of the vehicle because to be honest, there wasn't enough place to put it in the front. See, and the plug-in hybrid, the battery is much bigger, and we add a charger to charge the battery, so which is on the back of the vehicle also. Here, the emission, 32 grams CO2 per kilometer. This emission, it is very difficult to reach this emission because, to be honest, if the client charge really often, every day, its vehicle, and here the autonomy of this vehicle, I should have said first, with the battery put in it is around 40 kilometers in full electric. So if the client charge every day its vehicle and never drive more than 40 kilometers in a day, it means that he will drive in full electric every day. So the emission will be 0 grams CO2 per kilometer in its use. And on the other end, if the client never charge its vehicle, it means that the vehicle would, when the battery will be fully discharged, the gearbox will be managed as an hybrid vehicle. And here, as we said it on the capture, which is a little bit bigger than the Clio, the emission will be 108 grams CO2 per kilometer. So if you never charge, in the end, the emission will be 108 grams CO2 per kilometer. This 32 grams CO2 per kilometer is only the law, which tell us how we have to count the emission in full electric, which is 0, and in full hybrid, which is 108. And this formula depends on the autonomy in full electric. So here we consider we have 40 kilometers of autonomy, and so this is only a formula which take the 0 in full electric, the 108 in hybrid, and the 40 kilometers of autonomy, and the formula gives this 32 grams CO2 per kilometer. But again, here it is almost impossible to reach this emission, or to be honest, in fact, if you start to drive with a full battery, and if you drive I think it is almost 3 times the electric autonomy, you will reach this emission in mean on all the travel you did. So here in this case, if you drive 120 kilometers, you could reach this emission in mean. But okay, what I want to say is this is only a formula. What you have to know is that if you charge every day your vehicle, you can have 0 emission, but if you never charge, you will have in the end, with this car, 108 grams CO2 per kilometer. And even if you never charge, as we sell this car also without any hybrid gearbox. This car with a conventional thermal engine has emission of 120 grams CO2 per kilometer. So even if you never charge your plug-in hybrid, as you have the hybrid gearbox, the emission is a bit lower compared to non-hybrid engine. Okay, I just see this is the homologation autonomy, 65 and 50, but the WLTP cycle is consider that the driver is very calm and never make big acceleration. In nominal use, the autonomy will be 40 kilometers. Yeah, it's the same with pure EV vehicle. Yeah, in Renault we sell the Zoe. Now the Zoe was homologated with an autonomy of I think in the cycle we have 520 kilometer autonomy, but the real autonomy in normal use will be 450. So the cycle is a good way to compare different vehicle, but it's still not the real autonomy you will have by using the vehicle in normal condition. Okay. So here it is the same engine in the front of the vehicle, battery and charger in the back. Here we put the battery below the seat here, and the charger in the back, just to leave enough place in the back of the car. Which means that the seat is a little bit higher here compared to the non-hybrid capture, but still it is still acceptable. Okay. So now we'll go deeper in what we can do with this gearbox. In fact, this gearbox can be seen as two gearboxes combined. One gearbox with the IC, with the thermal engine, which can deliver 4 gears, and one gearbox with the main E-motor, which can deliver 2 gears. As I said, the second E-motor, the smaller E-motor, is always linked to the ICE. So with the second E-motor, we also can reach the 4 gears of the ICE line. Okay. So on the E-motor line, we have 2 gears. Gear 1, which is used from 0 to almost 80 kilometers, and gear 2, which can be used from 60 to maximum speed of the vehicle, in fact, which is 180 kilometers per hour. But because of the 50 kilowatt power, we consider that the E-motor can only be used alone to only to 130 kilometers per hour. If you want to go above, you will need to use both E-motor and ICE line. Okay, but still the E-motor can remain connected to the wheel and can be used with the ICE engine to reach the 180 kilometers per hour maximum speed. So one gearbox for the E-motor. If we compare to EV vehicle, now we don't put any gearbox on EV vehicle. It is only a simple reducer. Here we had to add this gear because if we don't have enough place to put a big e-motor in the gearbox, it means that with a smaller e-motor, we are limited with the speed of the e-motor, because to deliver enough torque, we have to increase the electrical frequency, and that's why we have to add those two gears, because here, if we want to remain in the first gear, we could lose the control of the main motor because the speed will reach to higher value. So here, when we change the gear of the e-motor, it only reduces the speed, but between 60 and 80 km/h, to be honest, the power we are already capable of reach the maximum power of the e-motor, which is 50 kW, which means that changing the gear doesn't change the maximum torque, and it changes the maximum torque because we reduce the speed, but it doesn't change the maximum power we can reach. So between 60 and 80 kilometers, even if we are on gear 1 or on gear 2, we can deliver 50 kilowatt of 52 kilowatt of electrical power. So it is only because of mechanical constraint that we add this gear to reduce the maximum speed we will have with this main motor, and to be able to have higher torque at low speed. Okay. And regarding the ICE line, we are able to reach 4 gears. We have the gear 2, 3, and 4, which are available with ICE alone. It means that we can have the main motor at neutral, and we can reach gear 2, 3, or 4 with the ICE line alone. But the first gear, in fact, is a coupling gear. It means that we connect the ICE to the main motor, which means that if the main motor gear is at neutral, we have only e-motor connecting to ICE, and that answer to the previous question I heard, means that the main motor can also be used as a generator to charge the battery if needed. But if we use this coupling gear and we connect the secondary, the main motor gear to the first gear, it leads to have an equivalent of a first gear to the ICE. So if you use this coupling gear and first gear here, we have a first gear on the ICE line. Do you have any question? No? You could have one, because as I said, if you use this coupling, you could have told me that if we connect the main motor on the second gear here, it could lead to a fifth gear on the ICE line, because as the ICE will be coupling to the e-motor and we change the gear of the e-motor, it is a new gear on the ICE line. But to be honest, it's not a fifth gear as we design our gearbox, because if we calculate the ratio of this combination of gears, it leads to the same ratio of the third gear here. So that's why we consider we have only 4 gears on the ICE line, but we have 2 different ways of reaching the third gear. In the future, we are redesigning our secondary gear here to be able to reach our fifth gear with this coupling and the ZEV2 connection here, because to have a better homologation result, we consider that this having a fifth gear can lead to better homologation result. But for now, if you buy E-Tech, you will have only 4 gears on the AC line. Okay, so do you know the difference between a parallel hybrid and serial hybrid? Maybe because this gearbox can work as both hybrid technology. A parallel hybrid means that thermal engine and e-motor is connected to the wheel in parallel. So here, if you connected the e-motor gear 1 or 2, and in parallel you connect the IC gear on any gear, you will have both motor connected to the wheel, which means that they can deliver power directly to the wheel. And we consider that this is the best efficiency in hybrid. But sometimes this gear can also work as a serial hybrid. As there isn't any clutch, it means that if we want to use the ICE at a very low speed, we cannot use it with the gear here. If you are at zero km/h speed, you cannot connect any gear on IC line because it will lead to IC speed of 0 RPM. And at 0 RPM, the IC cannot deliver any power. Whereas e-motor can deliver at 0 RPM. So here, with our gear, the only way to start the vehicle is by using the main e-motor. And as we have a second e-motor which is always linked to the IC, what we can do is start the IC and leave it in neutral, leave the gear in neutral, and use the second e-motor as a generator to deliver power to the high voltage system. This power can be directly used by the e-motor or can be stored in the battery. So at very low speed, or even at higher speed if needed, but as I said, if we can directly connect the IC to the wheel, it will always have a better efficiency than compared to a serial hybrid use, because in serial hybrid, the power comes from the thermal engine and goes to the wheel through two efficiency of the small e-motor, small generator, and then efficiency of the e-motor, of the main e-motor. If we connect the IC directly to the wheel, the power can go directly to the wheel, so only gearbox efficiency, which is always better. Here, our e-motor, the small e-motor has a better efficiency. Normally, the smaller the e-motor is, the higher the efficiency is. It cannot be true, but in general, it is like that. So here, with the small e-motor, we have an efficiency of 92–93%. Whereas on the main e-motor, we have an efficiency of 90%, 89–90%. Okay, so if we use the gearbox as a serial hybrid, we will have this efficiency of we have the IC efficiency first, but if we use the IC, we always have its efficiency, and then we'll have loss using the small e-motor, and then loss using the main e-motor. So that's why we use this gearbox with serial as a serial hybrid only at low speed when we cannot use it as a parallel hybrid. And as we use it only at low speed, that's why we don't need to have the generator motor, which is always linked to the ACE, that can deliver the same power as the main e-motor. I don't know, as you may know, but you could not know, Nissan sell a full serial hybrid vehicle in Asia. I don't think they can sell it in Europe, but in Asia and in the US, they sell a pure serial hybrid vehicle, which means there isn't any gear on the IC line. It is only the IC and the generator, and they put it on bigger car than us, so they put also a bigger e-motor, so they don't need to have a gear on the main e-motor. And as the power at any speed come from the IC and then through the first generator motor and at last to the traction motor, they put, in their case, the generator is the same e-motor as the traction motor. And they have, if I'm not wrong, and both are, I think, 80 kilowatt power. But if we compare with our gearbox, as the serial hybrid is only mandatory at low speed. At low speed, we don't need to have our 50 kilowatt power because we are limited by the maximum torque of the e-motor, and between 0 and 15 km per hour, the maximum power we could reach, if we consider the maximum torque of the e-motor, will be only a little less than 20 kilowatt. So that's why we have a smaller secondary e-machine which can deliver maximum 27 kilowatt, but in nominal 20 kilowatt. Okay.
Excuse me, so I have a question.
Yeah. Yes.
So for the parallel hybrid, so is it possible to activate the parallel hybrid mode during high speeds, or is it only restricted to the low speed? Because I see the synchronization of the motor and the engine speeds, it can be a problem during the high speeds because you have to bring both motor, like thermal engine and the electric engine, to the same speeds in order to couple them.
Yes. So here the question is about the coupling at high speed. Oh.
Yeah, like if you want to use the parallel mode, like parallel hybrid mode, like is it possible to use the parallel hybrid mode in high speeds?
So yes, it is, and this is by the way the only mode we are able to use. So at high speed, if we consider the maximum speed of the IC we can have, at high speed we can use only third or fourth gear, because and if we want to engage those gears, as you say, we have to synchronize the IC line speed to the right speed to be able to connect through the gear. So here, if I take the example of a speed of 130 kilometers, to engage the fourth gear, we will have to synchronize the IC speed to approximately 2060 RPM. 2600 RPM, sorry. And if you want to engage the third gear, we'll have to synchronize the speed to approximately 3500 RPM.
So as soon as we activate the parallel hybrid mode, like it will take some time to synchronize, let the RPMs match. Only then the actual function will implement on the car, right?
Yes, you understood well. In fact, if you are in pure ZEV at 130 kilometers, so here the gears will be 2, and the IC line will be in neutral. If you push the accel pedal, then you will ask for power. So the system will first choose if the third gear or the fourth gear is better for the power you request. If you fully push the accel pedal, it will lead to the third gear. So we will use the secondary e-motor to first start the ICE, and then when the ICE will be able to deliver torque, we will use both secondary motor and ICE to control the speed. And here we will control the speed till we reach the 3500 RPM. And when the speed will be reached, we will control the gear to clutch here to connect this third gear. And as the speed of the IC is already at the good value, there won't be any speed variation when we connect the gear. To be honest, using dog clutch technology, we need to have a small speed difference between the output of the gearbox and here the IC, because you will see I have some slide at the end, but dog clutch technology, the teeth of the dog clutch if the speed of the input and the output are the same, we can be locked on teeth-to-teeth position. So we need to have a small difference between input and output just to be able, just to ensure that we won't be locked in the teeth-to-teeth position, and that there is a small rotation between the input, between the dog clutch and the output. But the difference, we control it. We control a difference of 30 RPM. So here it means that if the speed of the IC when connected to the wheel is 3500 RPM, when we want to connect to engage the speed, we will control the speed of the IC to 3530 RPM. And then when the gear will be engaged, the speed of the IC will decrease from this 3530 to 3500.
Yeah, okay, got it, thank you.
Okay. So here is represented all the gear combination we can reach, but as I said, we have the 3 pure. Here we call it pure IC, 2, 3, and 4, but in fact we can never have pure IC, as there is the secondary e-motor always connected to the thermal engine. But if we consider it as a starter generator, we can say that those three gears are pure thermal engine gear. And if you can see both gears, we are in parallel mode. And if we keep this gear in neutral and we use only this, we have either pure EV if the IC is off, or serial hybrid if the IC is on. Okay. So here is a representation of what we are able to do. What is interesting with this gear is that as we always have two gears, and as we have two gears, one for IC and one for e-motor, we are able to ensure that there is always at least one motor connected to the wheels. Which means that when we change the gear of one motor or another, we always have another motor to deliver torque or power to the wheel. That's how we can reach same performance, same comfortability as dual clutch transmission, for example. Because when we change the gear, for example, let's imagine we are in this gear, so IC2 and EV1. So here we are connected IC2 and EV1. So the EV gear, the EV clutch, the EV dog clutch is here, and IC2 should be here. When we want to change here, it means that we go from IC to EV1 to EV1 pure and IC neutral. Then we can synchronize IC speed and go to EV1 and IC3. So if we were delivering power from IC and e-motor, when we declutch, when we disconnect the IC line from the gear, we can balance the power from IC to main e-motor, then synchronize the speed, and then balance again the power from e-motor to IC. This is how we ensure that the gear change can almost not be felt by the driver. To be honest, as the e-motor is limited to 52 kilowatt and the IC engine can reach 65, means that if you push the accel pedal, if you are at full throttle, you will lose a little bit of power during the gear change. So you could feel it, but if you drive not using the full power of your engines, those gear changes can be almost transparent during your drive. And this is the same when we change the gear from here, example, EV1 IC2 to EV2 IC2. Here we disconnect the e-motor. We can use the secondary motor and IC to deliver the power which was delivered by the main e-motor. Then we synchronize the speed of the main e-motor. We connect it through the second gear, and we balance again the torque from secondary motor and IC to the main e-motor. Okay. Just to inform you some difficulties we faced with this gearbox. When a motor is on, it implies that we cannot ask it 0 Newton meter, because as we have a gear connected, we need to ensure that the motor won't be free to move in the gear. So if we connect a motor through the gear, we have to ask it at least some Newton meter to ensure that it works either in motor or in generator mode. But we cannot connect the motor to ask 0 Newton meter. Here, with the main motor, it's simple, we can disconnect it, but here it is a difficulty because as the secondary motor cannot be disconnected from the IC, when the IC is on, we have to request either in motor mode or in generator mode to deliver power to the secondary motor. In nominal use, it is simple. We always use it as a generator, but sometimes we can imagine that this the battery of the vehicle is really full, and we cannot ask this motor to deliver power to the battery. And we cannot turn off the IC because of pollution constraint. Sometimes we cannot turn off the IC. And in this case, sometimes we have no choice but to cut the injection of the IC, remain and keep it in rotation by using the secondary motor as a motor. So it is constraint we have with this hybrid, and mainly regarding pollution and depollution homologation, because we have onboard diagnosis constraint. This is the onboard diagnosis constraint which can lead to not be allowed to stop the IC engine. Sometimes we have to make it run, even if we don't need it. As you understood, if the electrical battery is full, we would like to use only the main motor. So if you never start the IC won't start if the battery is full. But if you have started the IC because you request too much performance that cannot be delivered only by the motor, so you start the IC even with a full battery, and then sometimes because of onboard diagnosis constraints, you cannot stop it when you release the accel pedal and don't need any power. And in such case, we have to lose energy just to be able to perform our diagnosis.
Excuse me, like, can you give more detail, like why the IC should not be off in case if it is on?
I mean, as I said, we have to.
Yeah, I understand it's from the homologation standards, but there could be some reason why the IC should not be turned off once it is on. So,
in fact, the main reason are just to be able to perform diagnosis. Sometimes one simple diagnosis we have to perform is we have to measure, to estimate the loss of the IC. And the only way to estimate the loss of the IC is to make it run, but cut the injection. And we can estimate the loss by measuring how much power we need to keep the IC running at a certain speed. but without an injection. This kind of diagnosis can be performed like this.
So there
Also,
won't be any fuel consumption.
There won't be any fuel consumption at this time.
Oh, okay.
But what you have to consider is that when we lost electrical energy, if you charge the battery, it's not an issue. But if in the end the battery is empty, it means that all the energy you have lost in the past, you will have to deliver it from the ice, which is the only source of energy in the end. So the energy you lost at the beginning of your travel, you will pay it at the end.
Yeah, I understand now. Thank you.
Okay. So here it is for a plug-in hybrid, how we use the gear. As you can see here, we can choose between the fourth, third, or second gears depending of the level of power the driver is requesting. It means that if you ask for a few power, the fourth gear is enough. A little bit higher, the third gear, and if the speed is low enough, be able to use the second gear. Will perform a retro to use the second gear here. So here, this gear versus speed and power. Yes, there's no legend here. Here, you have to imagine that here, this is the speed of the vehicle, 0 km/h, 70 km/h, 130 approximately here, and 180 here. And here, this is the level of power requested, 0 here, and maximum power here, or maximum torque to the wheel, it's the same. Here it will be 6,000 Newton meter to the wheel here, maximum. And here it is negative value. As we have electrical motor, we never need to use the engine, the IC engine loss to brake the vehicle when you release the axle pedal. We will always use the main motor as a generator to make a feeling of IC braking as a conventional vehicle. Okay. That's why when the requested power is, or requested torque is below 0, we will, except if we have constraint again for diagnosis or pollution. If we can, we will always stop the IC when you release the axle pedal. And then if you push the axle pedal, we'll choose the IC gear almost as it could be chosen with dual clutch transmission. And here you can see that the EV gears, it's not the same because the constraint is only regarding the speed of the e-motor. As I said, if we are here, we are already limited by the 50 kilowatt power of the e-motor. And if we are here, we also are already limited by the 50 kilowatt maximum power of the e-motor. So changing the gear of the e-motor, the main e-motor, doesn't allow us to reach more power. It is only to respect our speed constraint that we change the gear. So that's why here it's only a speed threshold which leads to changing the gear of the main e-motor. Here I represent it as a simple one, but in fact we have hysteresis and so on, just to ensure that the gear won't change too fast. Okay. If you remain at this speed, we will choose one gear and keep it. Okay. And here, what you can see is a record of we perform on a car, storing vehicle speed and acceleration, which is the same of torque requested if we consider the road is flat. So as you see, at low speed, we are mainly in EV1 mode. And when the speed increases, we start to use parallel hybrid mode or only IC, again with a secondary motor, so almost pure IC, almost, but we still have a generator. So here IC2, parallel hybrid 2-1, and when the speed increase, we start to use the third gear and the fourth gear. Here you can see that even if I said that when we release the axle pedal, the objective is to use only EV gear, here you can see that it's not always the cases. There are two reasons for that. When you release the axle pedal, we need some time to disengage the IC line, and during that time we continue to respect the driver wheel. So those using of IC even with a deceleration request is only because of transitory mode, just to the time we need to disconnect the IC line. And the other use case is if the battery is almost empty. It means that when you release the axle pedal here, the maximum power you will generate with the main motor will be around 20 kilowatt. But if the battery is empty, we need to charge it just to be able to deliver the maximum power. Because if the battery reaches 0% of state of charge, it means we cannot use it to deliver power. So we always want to avoid to reach 0%. So if we are near the 0%, 1% and 2%, even if you release the axle pedal, we will keep the IC line connected just to be able to charge more the battery. Means that here the driver wheel is minus 20 kilowatt. We will keep the IC connected to deliver plus 20 kilowatt, and thus we can use the main motor to generate 40 kilowatt. So plus 20 from the ICE, minus 40 from the motor, means that the driver wheel is respected, minus 20 kilowatt, and we charge the battery with 40 kilowatt. So we are able to charge the battery and avoid, by doing so, we can ensure to avoid to reach the 0% state of charge of the battery. Okay. Here I plot what I explained a little bit before, which is a key point of this gearbox, is the torque balancing. As I said, when we want to change the gear from ICE2 to ICE3, if we want to do it really fastly, what we can do directly is just disconnect IC2, synchronize the speed, and then connect the IC3. But if we do so, it means that when we synchronize the speed of the IC line, there isn't any motor connected to the wheels. So it will not be so much comfortable. That's why when we want, even if we have only one motor connected to the wheel, and if we want to go from IC2 to IC3, we will transitory connect the main motor, in this case, So first, when you want to change the gear from IC2 to IC3, we will connect the main e-motor to through the second gear, through its second gear, for instance, so that when we want to disconnect the IC2, we can use the main e-motor to deliver power instead of the IC. So here in this phase, we use the main e-motor to compensate the future loss of the IC. Then during the IC spin synchronization, this is only the main e-motor that deliver the power. And then when the IC3 gear is engaged, we make the balance in the other way, which means that we decrease the main motor power and we increase the IC line power. And when the balance is fully finished, we can disconnect the main motor. Okay, yes?
Yeah, I have a small question here. So, can you please tell the time between the intersection point to the
Okay.
Yeah. So during this period, I see that the performance of the car will slightly reduce before the before the intersection point. So driver might feel like car is losing the speed or the performance, right?
Losing some performance, yes. If the power is if the power here is above 50 kilowatts, yes, means that as the EV power phase here is limited to 50 kilowatts, so there will be a small loss, yes. But if the power here is below 50 kilowatts, there isn't any loss, okay? But yes, you're right. It can happen. So here, if we want to have a time idea, when we want to connect the main e-motor to the wheel, it takes almost 300 milliseconds.
Oh, it's
so here you have to imagine that we are in ICE2, and at that time the system want to start the transition from ICE2 to IC3. So it is not represented here, but there will be 300 milliseconds to connect the EV, the main e-motor, to the wheels. Then balancing the torque from IC to EV. We are not able to do it so fastly because of comfortability issue. So if we consider the case of maximum power, so here if we are at 65 kilowatt, the time to balance here will be almost between 600 and 700 milliseconds.
Okay.
Okay. Then we synchronize the speed of the IC. It takes around 400 milliseconds. Then we balance again, so it takes again between 600 and 700 milliseconds, and then we stop the main e-motor, which take again 200 milliseconds. So here it means this complete gearbox change takes almost 2 seconds.
Okay.
But in these 2 seconds, we only have a loss of performance in these phases here of IC speed synchronization and the end of this phase and the beginning of this one. Because here we start from 65 kilowatt, we decrease, and here it is not represented, but you have to imagine that you reach the maximum 50 here. So then, beginning of here, you start to lose your 15 kilowatt. Here, during this 400 milliseconds, you have the 15 kilowatt loss. And then here it takes sometimes around a little bit less than 100 milliseconds to work, because here you will keep 50 kilowatt till the AC power goes above the 15, and then when the sum of both power has reached 65, we continue to increase the AC, and we start to decrease the main motor to keep the sum at 65. So here the total amount of time you can feel the loss of power, even if the gear change takes 2 seconds, it will be only between 500 and 600 milliseconds loss of power.
Oh,
But this can be felt. That's right.
yeah. Thank you.
Okay. But again, if the power requested before gear change is below 50 kilowatt, you don't feel anything during the gear change.
Okay.
You don't feel anything. You can the main motor speed we cannot hear it, but the IC speed we hear it. So you won't feel on acceleration point of view, you won't feel anything, but on noise point of view, you will hear that the IC speed change from one gear to another.
Mm-hmm. Yeah, thanks.
Okay. Here, I represent one issue also we faced when using our gearbox as a serial hybrid. When it is a serial hybrid, so we have the ICE, which deliver power, the secondary motor, high starter generator here, which is used as a generator, and in fact, which regulates the speed of both motor here, as they are always connected. So the inverter deliver power on the high voltage circuit. Here it is a battery. And this power can also directly be used by the main e-motor to drive the vehicle, to deliver power to the wheel. When we have a hybrid vehicle, it means that we have two circuits, one of low voltage, a conventional 14 or 12 volt circuit with a small lead battery, and the higher voltage. When we have those, we use a DC-DC converter to ensure that the small voltage network is always fed by the high voltage energy storage, because the main energy is stored in the battery. So we can feed the small lead battery by using this DC-DC converter and the battery. So it means that when here the generator delivers power to the high voltage circuit, it is used to charge the battery, to deliver power with the main motor, or also to keep this low voltage circuit fed with energy. Okay. So the power goes this side. So the speed control loop we designed. In fact, in serial hybrid mode, we have a charging power target, which means we want to deliver with the generator. It's some, I don't know, maybe 15 kilowatt power to the high voltage circuit. So what we calculate is that this 15 kilowatt power, we divide it by the IC speed, and we request this IC torque to the thermal engine. Okay. So this can be considered as a charging loop. The IC torque request is calculated only to respect a charging power target. And then we have a second loop with the starter generator, which is a speed loop. Here on serial hybrid mode, we will really often keep a low speed between 1,500 and 2,000 RPM, depending on the power. If you want to have a little higher power, we will increase a little bit the speed. But for noise acceptability, we remain at low speed when we work in serial hybrid mode. So here, you have to consider that we will control the speed at mainly 1,500 RPM. And we use the starter generator on a speed control loop because his response time is really faster than the ICE line. The ICE has a response time of maybe 300 milliseconds. That's also why when we balance the torque between the ICE and the main motor, as we said previously, it takes some time between 600 and 700 milliseconds because of this response time mainly. Whereas the e-motor and the starter generator here have a response time of 30 milliseconds. So if we balance torque between main motor and starter generator here and secondary motor, we are able to do it really faster compared to balancing torque between ICE and one or another e-motor. Okay. So here we calculate the starter generator torque request by this speed control loop. When we are in transitory mode, means that the ICE always respect its torque request, and the starter generator, if we have to increase the speed, can go in motor mode, or if we have to decrease the speed, will go in generator mode, and can go to almost minus 27 kilowatt power. If when we are at steady state, it means that we are at constant speed. So if the loop is stable here, if we request 15 kilowatt of power here to have a stable speed, it means that the HSG will deliver, consider if we neglect the efficiency, will deliver also those 15 kilowatt. So that's why here, even if we ask in open loop, the IC torque here, depending on the charging power target, it means that this charging power will be reached if we reach the steady state here, if we are able to stabilize the speed. But if there is any disturbance here, we benefit of the speed of the fast response time of the e-motor to control with the best efficiency here the speed. And you can compare, if you compare our speed regulation efficiency to a nominal, to an only IC speed control, here we are almost 10 times faster to control the speed with the high voltage starter generator compared if you want to control the speed with the IC. Okay. And what issue we face is that sometimes the battery cannot be charged anymore. There are some failure or some transitory states in which the battery the battery gives the information that we cannot charge it anymore. The main case is at a really low temperature, the battery cannot be charged. As here we are only in open loop, and the IC is not so much precise as we would expect, especially at low power. When the battery cannot be charged, it means that the charging loop here, we won't have other choice to ask a low power to the IC. And if there is a big gap of realization on IC side, it means that as we cannot violate the battery limitation, if we are not able to compensate the amount of power that is delivered in the DSC deliver more than we requested, it could lead to IC speed increase and loss of control. That's why we add a secondary loop which check if our speed loop here is near or not of the saturation of the minimum limit of the torque we can absorb. So here, if we are limited to, the same conversion, if we are the IC deliver plus 20 Newton meter, here we have to absorb, so we have to reach minus 20 Newton meter. But if because of the limitation of the battery, we are limited to minus 15 here, we face the issue. So with this number here, we know at the beginning that because of the battery limitation, we are limited to 15 Newton meter on this side. We take a little margin. We ask to the IC to deliver only 10 Newton meter. But because of error on the IC side, even if we requested 10 Newton meter, it delivers 20 Newton meter. So here on the speed control loop, we calculate the margin it remains on the SHG limit. As the speed increases here, we will fastly ask the SHG to go to its minimum torque, which will be minus 15. And because of this saturation, we will decrease the torque request on the charging loop. And in fact, we will this new loop will control the margin of the HSG torque between its actual torque and its minimum torque. So now we have two loops, one speed control loop and one margin control loop of the HSG torque. And this margin control loop can only reduce the torque request on the IC side. And so if we want to control 5 Newton meter margin on the HSG side, we will decrease the IC torque till the HSG torque will stabilize at minus 10 Newton meter. And so here, if you consider that the error of realization of the ice is 10 Newton meter at any time, it means that the final, in steady state, the final torque request to the IC will be 0 Newton meter. With its error, it will realize 10 Newton meter, and the HSG will absorb the 10 Newton meter. And we keep controlling this HSG torque request margin with its minimum to 5 Newton meter. So we have two separate loops, and that's how it works, because it would have been difficult to add in one speed control loop the two control, one of the HSG and one of the ice. Because we could have told also that we calculate the IC torque request depending on the speed control loop. But it means that we are not sure to control the steady state when the speed is reached. Maybe if the only aim is to control the speed, we cannot guarantee that the IC, that the charging power of the IC will be at the maximum that we can control. So that's why we split the control in two: speed control only on HHS side, and on IC side we add a saturation margin control of the starter generator. So, okay, maybe a bit late. I will go fastly on the dog clutch control, but here you can see how dog clutch looks. So you can see the teeth. Sooner, what I call the teeth to teeth here. You can see how we have to connect the gear. So the speed of the blue part is the speed of the wheel, and the speed of the red part here is the speed of the engine. If we want to talk simple. So here, if I take back the example at 130 kilometers, you imagine that this part is connected to the wheel. So the speed rotation here is correspond to maybe 3. If we want to engage the third gear, correspond to 3,500 RPM. So that's why we have to control the speed of the red part to the same speed, and then we can connect. And as you can see here, when we want to connect, if there is a small difference of speed, we can go in teeth-to-teeth contact transitory, and as there is a small displacement between the blue and the red here, in the end we will reach the hole and the entrance of the gear, as I could say, and this is the engagement. And what we use also is a spring assistance, just to be able to engage the gear even if the hole here is very, very small. The actuator is not so fast here. Yeah, in fact, when we want to move the actuator, so here's a fork which makes move here the dog clutch, it takes almost 80 milliseconds to move. But here, with 30 RPM different speed, it means that when we are in front of a hole, the time we are in front of a hole is approximately 7 milliseconds. So if the actuator here is too slow to be able to engage a speed in a hole, we will see 7 milliseconds, then teeth to teeth during 15 milliseconds, then hole 7 milliseconds, and so on. That's why we had this spring. So the actuator move. The spring is pressed when we are in teeth to teeth position, and when the spring is when we have this spring compression here, as the fork has really small inertia compared to the actuator here, the dog clutch can engage here in only 3 milliseconds. So as we are in front of all during 7 milliseconds, we have enough time to engage. Okay. So, do you have any question? It is a little summary of some of the issues we faced when we developed our technology, but there was a lot of. But no, there isn't any more question. Okay, Malek.
Yes, Ludovic, yeah. I don't know if there is any questions. Do you have Ludovic? You have finished, right?
Yes, I think
Yeah,
it's the time.
Yeah.
Excuse me, Professor.
Yeah.
Yeah. So I had a it's not a question but it's just a request that do you have any animated video or something for the engagement and the disengagement of this dog clutch management?
Yes, I can have some. I think I have some things. We'll try to find. Something here. No. This one. No.
Can I ask a question in the meantime?
Yeah.
Yeah, of course.
How much time does this development take? Like, how many people were involved?
Oh, it's a big question. On our side, when we start this project in 2011, and we start to sell the car in 2020. So you could say it takes almost 10 years. But it's not only because of technical issues that it takes a lot of time. It's because we have some political constraint between Renault and Nissan. Here I present the final design of the gearbox, but when we start the project, we had only one main e-motor, and we didn't have the high voltage starter generator. We have a conventional starter, because when we start the project, in fact, the aim was to sell it in our low-cost brand, which is Dacia, because our president didn't want at the time to design hybrid on Renault side. And then we talk with Nissan, and we use the Nissan motor, and we add the HSG. So it takes, I think, on technology side, all the control and all the system design, control design, it takes, if I put it all together, maybe 3 years, and the rest of the time is political discussion and where we will manufacture the gear, where we will manufacture the engine, and so on. And regarding the people, I'd say maybe personally, I work with an amount of, I would say 120 and 20%. Yes.
Interesting. Thank you.
Good. Okay. Another questions? So maybe I have one question from the chat, Ludovic. This question says, is it possible to achieve significant reduction of CO2 by implementing hybrid operation technology?
Significant, it is a big question. As I said, here with this hybrid, only with hybrid on the Clio, as I said, we have with conventional engine emission of 110 grams CO2 per kilometer, and tomorrow we will be able to reach with our hybrid the same ICE, but hybrid gearbox and e-motor. We will reach 88 grams CO2 per kilometer, which means that we are able to reduce, but significantly. This is a big question. If you consider that this 20% reduction is significant, it's your point. As the aim is in the end, we will be requested to reach zero. Hybrid using thermal engine is only a transitory technology.
Yeah.
Okay, I found the video.
Yeah.
I have one, like, it's not related to the topic, but the research work. So I know Renault Nissan has a Formula E car. So is the Formula E technology group is at Renault France, or is it in different area?
Can you say it again? Sorry.
Yeah, I know that the Renault Nissan has a Formula E team, right?
Yes, it's mainly Renault, but yes.
So the technology center
the Formula E team is.
Yeah.
The center is in France. It is in Vélizy. So not really sure, but it is in the southwest of Paris.
And is it open for the students like us for the masters, or is it specifically constrained to some PhDs or something like that?
To be honest, I don't really know. I know that there is a Renault Foundation that are looking for masters, maybe for sure like you, but I don't know if there are availability or opportunities on Renault Formula 1 or E Formula from this foundation. Personally, I work in main center, in Techno Center here in Guyancourt, and I know that we have some students coming from many places, but I don't know. To be honest, I don't know on Formula 1 if there are availabilities. Yeah.
Okay, no problem. Thank you.
So here, do you see my screen? Here the video?
Yes.
Okay. So here you can see, just to show. So here, this is the main e-motor. Here, this is the dog clutch. So here, we connect on the left for gear 1, on the right for gear 2. Here, the IC line, which is connecting to the second e-motor. We have gear 2, gear 4, gear 3, and coupling here with the main e-motor. So here, when we start the vehicle, we want to connect the first gear here. So, and then when the main e-motor turns like this, we want to change the gear. We go to neutral, speed synchronize, and go on the other side. And there is the second speed. So here in this video, we are in pure ZEV mode. But this is basically how it works. I don't know if the video was good on your side. But this is basically how it works. Yeah.
I have a question.
Yeah, of course.
The control of this gearbox is, let's say, automatically, or the user can decide like some configurations according to
it is
their
fully automatically. The user cannot, as I said, in fact, this gear, it is 2 gearbox in parallel, one for the motor, one for the ICE. When we change the gear from one gearbox, we use the other to compensate the loss of torque. It cannot be managed by the driver, in fact. And we have other constraints. In hybrid, we have to ensure that the battery will never be empty. So the control of the state of charge of the battery also creates constraints in the choice of the gear we'll keep. As I said, if possible, when you release the accel pedal, we'll only use the e-motor to generate. But if the battery is low, we will keep the IC engaged to generate more. This function cannot be done by a driver. The driver won't check the state of charge of the battery to engage the right speed. So no, it is fully automatic. It's fully automatic.
So the user cannot put like a racing mode or a green mode to use.
In this way, if you have a PHEV, a plug-in hybrid, we have a full EV mode, which means that if the state of charge is high enough, we'll only use e-motor. But even if you request a full EV, if you push the accel pedal at full throttle, we will still start the IC. But if the driver requests EV mode, we'll try to respect and use only the e-motor. And we also add what we call a sports mode. In sports mode, the difference is the state of charge of the battery we control. We try to keep it at a higher level compared to nominal use, just to be able to deliver more power at any time. And in sports mode also, we keep the IC on at any time, because if the IC is already on, we will be able to engage a gear fastly compared to if the IC is off. So this is the main difference between nominal hybrid mode and sports mode. And as the IC is on and the gear will be engaged fastly, the torque response of this global engine will be faster.
Wonderful. Thank you very much, Ludovic.
Very good, yeah.
Hi.
Yeah.
I'm Marcus. I would like to ask you, Ludovic, about I think it's like a personal and professional matter. I saw that you are graduated. You have like a master degree from Centrale Supelec, I think, and in mechatronics, robotics, and automation engineering. And I
Yes.
would like to know, for your personal point of view, how this master helped you to get this position at Renault, and how do you, and what do you think about like for us new masters, how this masters at the call Centrale may help us to enter in this field of electrical vehicles?
Okay. Personally, so I was student in Supélec. I made several internships in for the CEA, I don't know, where I work on drone control. And I made my final internship in Renault, where I work on braking system. And so to me, I think that the professional experience of those internships is really important to choose here, yeah, because in Renault we have a lot of internship, and some of them are then we give them a job after the study. So to me, I would say that you have to find at the end of your master the right company or the right field you want to work in, because I think it is really easier to get a job if you already are in the company at the end of your study. And maybe don't hesitate to do several internships in different companies if you either if you don't like what is done in the company, or either if unfortunately there isn't any place in the company you want to enter.
Okay, thank you. Do you think, like, I mean, in your experience, what you see in Renault, if a person with a master has let's say a preference in the matters of getting a position in the company, or if in comparison with the person with a bachelor, let's say?
Oh, here in Renault Techno Center, a master is almost mandatory. We have only my colleagues. We are all at least master or PhD.
Okay.
Or PhD.
Good to know.
That's it.
Okay, thank you.
Very good. Okay, there is another questions. If you have another question, don't hesitate to ask them.
Okay, so
I don't know if,
thank you, Malek, for allowing me to present this topic. So that was a pleasure.
Yeah, thank you very much, Ludovic, for coming today to give this nice talk about hybrid electrification on Renault cars. It's really very, very interesting. And I think we will have more collaboration about it, including our E-PiCo students.
Okay.
Okay, so
thank you very much.
Thank you, and see you next
Thank
time.
you. Yeah, have a good lunch.
Yeah, good lunch. Yeah, thank you.
Goodbye.
Goodbye. Okay, so we have to finish here this morning session. And have a good lunch and see you at 2 p.m.